this video, we're going to begin discussing what happens where we have continuous random variables. We've already discussed discrete random variables. Now we're going to be discussing continuous random variables. When we talk about continuous random variables, if they are all equally likely to happen, those are called the uniform probability distribution. And when we're talking about the uniform probability distribution, recall whenever we were looking at the histograms earlier on and everything was the same height. So if I look at a histogram, if everything is the same height, that's a uniform. That's a uniform, and if we use relative frequency or their probability, that would be the probability distribution. Well, most things are not going to be uniform or anything like that. So a probability density function, let me write this in, probability density function, is an equation used to compute probabilities of continuous random variables. The thing is it must satisfy a couple of things. Underneath that curve must all equal up to 1. Recall whenever we were talking about probability distributions in themselves, each probability distribution had to add up to a total of 1. Same thing here whenever we're looking at the probability distribution curve. The height of the graph of the equation must be greater than or equal to 0 for all possible values, meaning we can't have just a 0 value. What we're looking at is similar to those normal curves that we've looked at, the ones that are symmetric on both sides. So let's look at the normal curve. This one is the normal curve, and whenever we look at a normal curve, what we're looking at is, say here is our mean, and it goes the same way both directions. It's that bell-shaped. We can fold it over on top of itself. So whenever I look at this, what we're discussing is that the area, recall whenever we were using the empirical rule, this in here constituted as 68% of our data. So the probability of getting within here is going to be 0.68, because we know that between one standard deviation on both sides of the mean is that 68% of our data. Now, a continuous random variable is normally distributed or has a normal probability distribution. So whenever we're looking at it, we think of it being symmetric. That should be an L, not a T. If the relative frequency histogram of the random variable has the normal shape. So if we draw a histogram with using the relative frequency instead of just the frequency, it should come out to be a normal curve. Again, in the center is the mean, therefore anything to the left of that center constitutes 50% of your data, which has a probability of 0.5. Same thing happens on the right side. Now you'll notice that here I've got one standard deviation marked on both sides. Therefore, between those two values is 68% of our data, and it has a probability of 0.68. So let's look at the properties of a normal curve. Well, first of all, it is symmetric about its mean. So where we have it, the mean is in the center, and I can fold it over upon itself. Secondly, the mean, the median, the mode is a single point. It's the highest. Remember when we were back talking about mean and median, and we said if the mean was greater than the median, then it was going to be skewed right. If the mean was less than the median, it would be skewed left. Well, in a normal curve or a bell-shaped curve, those things are going to be equal to each other. It has inflection points at mu minus sigma and mu plus sigma. So these points right here, those are what we consider inflection points. The area underneath the curve adds up to 1. The area under the curve to the right of mu equals the area under the curve to the left of mu, which equals 1/2. So in other words, if I draw a line down the center, this is half and this is half over here. As x increases without bound, means it gets larger and larger and larger, the graph approaches but never reaches the horizontal axis. Therefore, this line right here actually gets as close to our horizontal axis as possible, but it never touches it. The reason for that is the fact that we don't know where those larger values are. There's always going to be that very slim possibility. So it's still got to have some probability, not equal to 0. Same thing happens on the left side. Now the empirical rule, if you will recall, was used for the bell-shaped data. Any bell-shaped data had the 68, 95, 99.7 rule, the empirical rule. This is extremely true with these continuous variables, and so we redraw that shape, and we have that between the mean and one standard deviation is 34%, or 0.34. And keep on going. As we go further and further outside, we get to as close to 100% as possible. We never actually get to 100% though. Okay? So a normal distribution can have any mean and any positive standard deviation. But a standard normal distribution is one that we have normalized. It's one in which we have taken the others and made them into the same. Its mean is 0 and its standard deviation is 1. When we talk about normalizing it, what we're doing is we're looking at it value in comparison to the rest of its data, in comparison to its mean, in comparison to its standard deviation. So we're looking at a z-score. Anytime that we talk about the standard normal distribution, we're talking about a z-score. A z-score has that mean of 0. It's in the center. And remember that mean in the center of the z is going to be 0. I can be positive or negative, going left or right. And so our standard deviation for this is just going to be 1. If we look back at the previous picture, if I put a 0 here, this would be positive 1, positive 2, positive 3. This is negative 1, negative 2, negative 3. That's what we mean whenever we want to normalize something using that standard normal distribution. In the next coming videos, we're going to be looking at table A2. So if you have not had a chance, I would go ahead and get a copy of table A2. This is going to help us look up those probabilities. Okay? So go ahead and get a copy of that. and then we'll look at this in the next video.